continuation of our discussion yesterday we had, would like to continue the discussion of the states of matter. What are the things we have to discuss today? Types of intermolecular forces. Types of intermolecular forces. Types of intermolecular forces. So, what type of intermolecular forces that are likely to exist? Why we need to discuss about the types of intermolecular forces? Because the type in the strength of the intermolecular forces will decide the behavior of the behavior of the gases depends upon the strength of the intermolecular forces. Now coming to the first type, ion dipole. This type of the intermolecular force, this type of the forces will exist between an ionic compound and a polar covalent compound. Ion dipole type of forces will exist between an ionic compound and a polar covalent compound. Next, dipole interactive forces. Interactive forces. This type of the force of attractions will exist among the polar covalent compounds. Now, dipole and induced dipole attractions. Dipole and induced dipole. The first one is ion dipole, which is likely to exist between an ionic compound and a polar covalent compound, and dipole type of interactions are present among the polar covalent molecules. Dipole and induced dipole type of attractions exist among a polar covalent compound and non-polar covalent compound. In polar covalent compound, permanent dipole will be present, which will introduce a temporary dipole among the non-polar compound. Next, among the non-polar covalent compound, the type of forces are called London dispersion forces, or we can popularly call as Van der Waals force of attraction. In this type of the force of attractions exist among the non-polar covalent molecules. What happens? How this type of the force of attractions are generated? So normally what will happen? The distribution of the electrons around the nucleus will be symmetrical. For a moment, the symmetrical distribution of the electrons around the nucleus will get dispersed, leading to the formation of a temporary dipole. So when we consider helium or any other non-polar covalent compound, first temporary dipole will be induced, because momentarily when the symmetrical distribution of the electrons around the nucleus gets disturbed, it leads to the formation of a temporary dipole. This temporary dipole will induce another dipole in the neighboring molecule. So this type of the forces are called induced dipole and induced dipole interactions. And strength of the London dispersion forces will increase with increase in the size of the molecule, or with increase in the molecular weight. Among the hydrocarbons, with increase in the length of the chain, strength of the London dispersion forces will increase, leading to the higher boiling point. Among the alkanes of the same molecular weight, If there is a branching take place, due to the branching, what will happen? The surface area decreases. When the surface area decreases, the strength of this type of the London dispersion forces will be reduced. This is briefly about the strength of the types of intermolecular forces. Now another point we have not discussed yesterday is the types of molecular velocities. Types of molecular velocities. What are the types of molecular velocities we have? We have three types of molecular velocities: most probable velocity, average velocity, and RMS velocity. What is the point? At any given temperature, all the samples of all the molecules of a sample of gas do not move with the equal velocity. Why they do not move the same velocity? Due to constant collisions with either other molecules or also the container That is why different types of molecular velocities are proposed. And this is RMS velocity, this is the most probable velocity, this is the average velocity. What do you mean by most probable velocity? What is meant by most probable velocity? The velocity possessed by maximum number of the molecules in a sample of gas is called most probable velocity. Magnitude wise, what is the order of the velocities? Magnitude wise, RMS velocity will have the higher magnitude, followed by average velocity, followed by most probable velocity. Number wise, Cp greater than C bar greater than C. What is the relation between the Cp and the RMS velocity? Cp will be equal to C into 0.8166 and C bar is equal to C into 0.9213. With increase in the temperature, the magnitude of the most probable velocity increases, but the fraction of the molecules moving with the most probable velocity decreases. So this is briefly about the types of molecular velocities. Now what is the point? In general, what is the point to be remembered? C is proportional to root T by m. What is C? It is broadly taken as the molecular velocity. C is proportional to the square root of T by m. C1 by C2 is equal to T1 by m1 into m2 by T2. T2 by m1 m2 by T2. Using this relation, we can crack the numericals. What is the other point we have to discuss regarding the critical constants? What do you mean by critical constants? PC, VC and TC. What is most important point? TC. What do you mean by TC? Critical temperature. How to define critical temperature? The temperature above which gas cannot be liquefied, whatever be the magnitude of the pressure we have applied. That is a TC. And what is VC? Critical volume. And what is PC? Critical pressure. So volume occupied by 1 mole of the gas at the conditions of TC and PC is called critical volume. What are the expressions for PC, VC, TC? A by, in terms of Van der Waals constant, A by 27B square. What is VC? 3B. What is TC? 8A by 27 RB. Now what is PC, VC by TC? PC, VC by TC will be equal to 3 by 2 or 3 by 8 R. These are the values of PC, VC, TC. Now let us come to the discussion of the questions. Two glass bulbs A and B are connected by a very small tube having a stopcock. Bulb A has a volume of 100 ml contained the gas, while bulb B was empty and has a volume of 150 ml. Opening the stopcock, the pressure of the gas in the bulb will fall down. Here the temperature will be maintained constant. So since the temperature is maintained constant, we can simply apply the Boyle's law. What is the here? The bulb, two bulbs are there. Now the bulb A has the volume of 100 ml and bulb B has the volume of 150 ml. On opening the stopcock, what will happen? The final volume will become 250 ml. So P1 V1 is equal to P2 E2, simple Boyle's law. So P1 P, what is V1? 100 ml. What is P2? What is V2? 250 ml. Because when the stopcock is open, the gas will occupy both the bulbs. The volume will be 250 ml. Then what will be the final pressure? P2 will be equal to P into 100 by 250, that is equal to P by 2 by 5. So P by 2 by 5, that is 0.4 P. So the volume of the pressure, the final pressure will be fall down by, if you calculate into the percentage, it fell down to 40%. Option 3 is answer. Next, at 298 Kelvin, 10 liters of nitrogen at 0.96 atmospheres is added to 32 liters evacuated polyethylene bag. Subsequently, enough oxygen is pumped into the bag at 298 Kelvin. Now, if the total pressure is 0.990 atmospheres, the partial pressure of the oxygen is, this is simple Dalton's law of partial pressure. P total is equal to partial pressure of the nitrogen plus partial pressure of the oxygen. Now the question is, we have to calculate the partial pressure of the oxygen. What will be the partial pressure of the oxygen? Total pressure minus partial pressure of the nitrogen. P total value is equal to 0.99 atmospheres. Now we have to calculate the partial pressure of the nitrogen. How to calculate the partial pressure of the nitrogen? P initial and multiplied by V initial by V final. Applying how this formula is obtained, just this is the application of the Boyle's law. So what is P initial for pressure initial? 0.96. What is V initial? 10 liters. And what is the V final? 32 liters. So it comes to 0.3 atmospheres. Partial pressure of nitrogen comes to 0.3 atmospheres. Then partial pressure of the oxygen will be equal to 0.99 minus 0.3, which is equal to 0.69. Option 1 is the answer. Just it is an application of Dalton's law of partial pressure. We got the total pressure. We have calculated the partial pressure of the nitrogen applying Boyle's law. Then we got the partial pressure due to oxygen. Next question. So initially what is given? Rate of effusions of two gases are given. RA by RB is equal to root of MB by MA, which is equal to 2:1. This is given. Now what is the ratio of RMS velocities if TA and TB are in the ratio of 2:1. So RMS velocity of CA by CB will be equal to root 3 RTA by MA, root 3 RT by MA into MB by 3R TB. 3R TB. 3R gets cancelled out. 3R gets cancelled out. Now root of MB by MA is equal to 2. What is left over? We can write like this: root of MB by MA into root of TA by TB. What is root of MB by MA? 2 by 1. What is root of TA by TB? So the answer is option 3 is the answer. Just they have given ratio of rates of diffusion. They have, what is the question? CA by CB is equal to how much? Now MB by MA is equal to 2 by 1 and TA by TB is also equal to 2 by 1. So this is the way to solve it. Just next question. Van der Waals constants for 3 different gases are given. Now we are asked to find which statements are correct. What is the point here? Higher the value of A. What do you mean by higher the value of A? Higher values of A indicate that intermolecular force of attractions are strong. When intermolecular force of attractions are strong, such gases can be liquefied easily. So for easily liquefiable gases, critical temperature will be maximum. What do you mean by higher values of A? Indicate that strength of intermolecular force of attractions is high. When strength of intermolecular force of attractions are high, the intermolecular gap can be reduced easily. That means the gas can be liquefied easily, and easily liquefiable gases will have, by default, will have higher critical temperature. So option 1 is correct. And why gas, or what is the option 2? So among the 3 gases, a gas X has the most ideal behavior. Why gas X has the most ideal behavior? Because for it the Van der Waals constants are very less. Van der Waals constants are relatively low. So when Van der Waals constants are relatively low, implies that the gas has more ideal behavior when compared with the other 2 gases. Next, what is the other statement? Maximum molecular volume. Which gas has the maximum molecular volume? So gas Z has that, because what is the molecular volume? Vc will be equal to 3b. So higher the value of B, greater will be the molecular volume. So all the 3 statements are correct. Higher the value of gas Y has higher A value, so it is easily liquefiable and has high critical temperature, and the gas X has the low Van der Waals constants, so its behavior will be close to ideal behavior when compared with the other 2 gases. Gas Z has the higher B value, so when value of the B is more, the volume occupied by the molecule will be more. All statements are correct. So option 4 is the answer. Next question. The relation between PCVC by TC is equal to root 3 by 8 R, because what is the PC value? PC value is equal to A by 27b square, Vc value is equal to 3b, and Tc value is equal to 8a by 27rb. If you substitute these values in the above expression, we get that value. PCVC is equal to PCVC by Tc is equal to 3 by 8 or PCVC is equal to 3 by 8 or Tc. Option 4 is the correct answer. Next question. So the values of critical volumes are given. So Vc is equal to, what is the point when critical volumes are given? What does it imply? Vc is equal to 3b. Vc is equal to 3b. In the given set of the gases which has the higher critical volume, gas D has the higher critical volume. So automatically the B value will be more. The B value will be more. So it will have larger diameter. The B value is more. It will have the larger diameter. Larger diameter. Option 2 is the answer. So this is goes by the definitions. What is the critical temperature is given by the expression 8A by 27 RB. What is Boyle's temperature? The temperature at which gases tend to behave ideally, which is given by A by RB. What is inversion temperature? Inversion temperature is given by the expression 2A by RB. And what is reduced temperature? So reduced temperature is given by T by Tc. Similarly, reduced volume is V by Vc. Reduced pressure will be equal to P by Pc. Why these are called reduced pressure, reduced temperature, reduced volume, reduced pressure? These terms are used to eliminate the van der Waals constants A and B from the gas equation. That is why they are called reduced conditions. Answer is S. A is for S, B for P, V for P. Boyle's temperature is A by RB, and inversion temperature is for C it is Q, for D it is R. So for D it is R. Okay. Option 1 is the answer. So compressibility for ideal gas, for compressibility factor for ideal gas, Z is equal to 1. For an ideal gas, Z is equal to 1. At medium pressures, or at moderate pressures, as we have stated that Z is equal to 1 minus A by RT, A by V RT at moderate pressures. At very high pressures, Z will be equal to 1 plus BP by RT. Next, Z at for critical state, A for compression factor for an ideal gas is 1. So for A it is R. For Z for real gas at low pressure is, for B it is S. For B it is S. For C it is, Z for real gas at high pressure is Q. 1 plus BP by RT. At critical state, Z will be equal to 3 by 8, because PCVC by Z is equal to PCVC by RTC, which will be equal to 3 by 8. Option 3 is the answer. Next question. A gas occupies a volume of 2.5 liters at such as 9 into 10 to the power 5 newtons per meter square. What is the additional pressure required to decrease the volume of the gas to 1.5 liters, keeping the temperature constant? This is nothing but application of the Boyle's law. P1 V1 is equal to P2 V2. So additional pressure required is equal to P2 minus P1. What is P1? 9 into 10 to the power 5. What is V1? 2.5 liters. What is P2? We have to calculate. What is V2? 1.5 liters. From this, P2 will be equal to 15 into 10 to the power 5. So additional pressure required is 15 into 10 to the power 5 newtons per meter square minus 9 into 10 to the power 5, which is equal to 6 into 10 to the power 5 newtons per meter square. And newtons per meter square is the SI unit for the pressure. Next question. Now we're asked to compare the densities at foot of the hill, at the foot of the mountain, at the top of the mountain, temperature at and pressure is, whereas the ratio of the densities, we know that D is proportional to P by T. For a given gas, D is proportional to P by T. At the foot of the mountain, what are the values? At the foot of the mountain, D comes to at foot of the mountain, D comes to proportional to 760 mm. 760 mm means 1 atmosphere. 760 mm by, what is the temperature? 30 degrees 303. At the top of the mountain, what are the values? D is proportional to 710 by, what is the temperature at the top of the mountain? 273. 710 by 273. So mathematically D1 by D2 will be approximately equal to 1. This is D1, this is D2. So the ratio of D1 by D2 will be approximately equal to 1. Option 4 is the answer. Next question. Here, what are the next question? What is the equation of the state? P1 V1 by N1 T1 is equal to P2 V2 by N2 T2. So what they have said, pressure is maintained constant. Since the same vessel, volume is also maintained constant. So N1 T1 will be equal to N2 T2, because pressure and volumes are constant. Because since pressure and volumes are constant, what will be the relation? N1 T1 will be equal to N2 T2. For a given gas, N1 is proportional to W, because molecular weight remains the same. W1 T1 is equal to W2 T2. W1 T1 is equal to W2 T2. What is W1? 4. What is T1? T. What is W2? Because 0.8 grams is removed. So W2 will be 3.2. And what will be the T? T plus 50. Solving, T is equal to 200 Kelvin. option 1 is the answer. Here what are the parameters that are kept constant? Pressure and volume. Then this relation will be reduced to N1 T1 is equal to N2 T2. For the same gas, since molecular weight is same, number of moles will be proportional to the weight. Number of moles will be proportional to the weight. Then final equation is W1 T1 is equal to W2 T2, and this is the relation. Next question. Here LPG cylinder. Here what are the variable parameters? And weight of the gas, and the pressure. What are the variable parameters? Mass and the pressure. Mass and the pressure for a given gas. What are the maintained constant? Volume and temperature are kept constant. Volume, temperature are kept constant. Therefore, P1 V1 by N1 T1. This is the relation. What are kept constant? Volume and temperature are kept constant. Therefore, P1 by N1 is equal to P2 by N2. For the same gas, the relation can be written as P1 by W1 is equal to P2 by W2. P1 by W1 is equal to P2 by W2. So 15 kgs initially what is the pressure? 10 atmospheres pressure. And initially what is the weight? 15 kg. What is the final pressure? 8. W2 is equal to, solving, W2 will be equal to 12 kg. So the weight of the gas that is leaked out is W1 minus W2, 15 minus 12, 3 kg. So this is the relation. This is the way to do it. Answer 3. Next question. So, in what ratio by mass carbon monoxide and nitrogen should be mixed so that partial pressure exerted by each gas is same? Partial pressure exerted by each gas should be same. So, for the partial pressure of the CO to be equal to the partial pressure of the nitrogen, what should be equal? Mole fraction of the CO must be equal to the mole fraction of the nitrogen. So ratio of mole fractions will be equal to number of moles. Ratio of mole fractions must be equal to ratio of the number of the moles. So what should be the ratio? W of CO by molecular weight of CO into molecular weight of nitrogen by weight of nitrogen. These two are equal. What is the molecular weight of carbon monoxide? 28. What is the molecular weight of nitrogen? 28. So is equal to 1. So weight of carbon monoxide by weight of nitrogen should be equal to 1. So what is the point? For the partial pressures to be equal, what is the necessary condition? Mole fractions to be equal. So by definition, ratio of mole fractions is equal to ratio of number of the moles. Since molecular weights are equal for carbon monoxide and nitrogen, the weight ratio should always be equal to 1. So option 4 is the answer. Next. Here this is simple ideal gas equation application. Simple ideal gas equation. What is the ideal gas equation? The total pressure of the gases mixture will be equal to sigma n RT by V. Sigma n RT by V. What is sigma n? number of moles of sigma n is equal to number of moles of oxygen plus number of moles of hydrogen. 3.2 by 32 plus 0.2 by 2, it comes to 0.2. So total pressure will be equal to 0.2 into 0.0821. And what is the temperature? 0 degrees centigrade, 273. And what is the volume? 1.12 liters. 0.0821 into 273 is 22.4. So this comes to, the total pressure comes to 4 atmospheres. It is a simple ideal gas equation. Next question. Now coming to the kinetic energy. What is the expression for the kinetic energy? What is the expression for kinetic energy? Ke is equal to nRT. K is equal to nRT. Since R is constant, Ke1 by Ke2, Ke1 by Ke2, Ke1 by Ke2 is equal to N1 or T1 by N2 or T2. R gets cancelled out. R gets cancelled out. How do you get number of the moles? Number of molecules by Avogadro's number. So number of moles is also proportional to the number of the molecules. What is the Ke1 value? X joules. What is the Ke1 value? X joules. What is the N1? What is the number of the molecules? N. What is the temperature? T1. Minus 123 degrees centigrade means 150 Kelvin. 150 Kelvin. What is the Ke of the second sample of the gas? 2x. Here let the number of the molecules of the second sample of the gas is taken as Z. And what is the temperature there? What is the temperature in the second condition? 300. So Z also will be equal to N. Z also will be equal to X gets cancelled out. 2 gets cancelled out. So Z is equal to 1. Z is equal to N. So the second sample also contains same number of the molecules as that in the first sample of the gas. Option 1 is the answer. Next. Here this is also related to the kinetic energy. Kinetic energy is equal to nRT. Kinetic energy is equal to nRT. 3 by 2 nRT. 3 by 2 nRT. So 3 by 2 nRT. What is the expression for kinetic energy? Kinetic energy is equal to 3 by 2 nRT. 3 by 2 nRT. But nRT is equal to PV. nRT is equal to PV. Therefore, kinetic energy is equal to 3 by 2 PV. 3 by 2 PV. So 3 by 2, what is the P value here? What is the P value? 5. And what is the V value? 4. It comes to 30. It comes to 30. Option 4 is the answer. So PV is equal to nRT. PV is equal to nRT. PV is equal to nRT. When a graph is drawn between PV versus T, what will be the slope? Slope will be equal to NR. What will be the slope? Slope will be equal to NR. And so what is the value of N? 8 by 4. R value 0.0821. So it will be 0.1642. So option 3 is the answer. Simple. PV is equal to nRT. When a graph is drawn PV and T, what will be the slope? nR. So this is the value of nR. Next question. A 10-liter vessel contains helium gas at 10 atmosphere and T Kelvin. How many balloons of 1 liter capacity at 1 atmosphere and 2 to K can be filled by using gas present in the cylinder? Here also number of the balloons, what is the formula? Because when pressure is reduced, volume increases, the excess volume will come out of the cylinder. The excess volume of the gas that is flowing out of the cylinder can be used to fill the balloons. So number of the balloons that can be filled is equal to excess volume by volume capacity of the balloon. What is the volume capacity of the balloon? It is 1 liter. It is a 1 liter. What is the excess volume? Excess volume is equal to, excess volume will be equal to V2 minus V1. Now let us first try to calculate the excess volume keeping at the same temperature, applying a Boyle's law. P1 V1 is equal to P2 V2. P1 V1 is equal to P2 V2. Maintaining the same temperature, at same temperature T Kelvin, we are calculating the excess volume at the same temperature. So 10 into 10, and what is P1? V2. So V2 is equal to 100 liters. What is the excess volume at the same temperature? Excess volume at a T Kelvin is equal to 100 minus 10, 90. Now when the temperature is doubled, the excess volume also gets doubled. Excess volume, applying Charles' law, excess volume at T2K Kelvin, excess volume at 2T Kelvin will be equal to 180 liters, because they are asking us how many balloons can be filled at the temperature 2T Kelvin. Excess volume at the same temperature is 90 liters. Excess volume when the temperature is doubled will be 180 liters. Now how many balloons can be filled? Number of the balloons that can be filled is 180 by 180. That is a point to be remembered. Now the excess volume at higher, double the temperature, excess volume at 2T Kelvin will be equal to 180. So number of the balloons that can be filled will be equal to 180 by 180 balloons. Option 3 is the answer. What is the point? What is the twist they have given? We have first calculated the excess volume at the same temperature. Now we have to calculate the excess volume at the double the temperature. At double the temperature, excess volume will be 180, and number of the balloons that can be filled is equal to excess volume by volume capacity of the balloon. So option 3 is the answer. See, and in the given set of the molecules, for the intermolecular force of attractions are certainly stronger in case of the water, because what is the type of the force of attractions that are likely to exist among the water molecules? Intermolecular hydrogen bonding. And what are the type of the force of attractions among the other molecules? They are nothing but van der Waals force of attractions. certainly hydrogen bonding is stronger than van der Waals force of attractions. The remaining are non-polar covalent molecules. Among non-polar covalent compounds, what is the type of the force of attractions that is likely to exist? Nothing but van der Waals force of attraction. What is the type of force of attractions among the water molecules? Hydrogen bonding, which is certainly stronger. So option 1 is the answer. Here the London dispersion forces of attractions will increase with increase in the size, length of the chain among the given compounds, n-hexane, n-pentane, isopentane and neopentane, which has the larger chain length, n-hexane, and which has the highest molecular weight, n-hexane. So option 1 is the answer. Two flasks of equal volumes have been joined by narrow tube of negligible volume. Initially both the flasks are at 300 Kelvin and totally 9 moles of gas is present. One of the flasks is then placed in a thermostat of 600 Kelvin. How many moles of the gas is present in the hot bulb? So when initially what will happen? Both bulbs are two flasks are equal volumes. Initially both the flasks are maintained at 300 Kelvin. Both the flasks are maintained at 300 Kelvin. When they are maintained at 300 Kelvin, so the pressure will be uniform. Both the flasks will have the equal number of the moles because volume is same, temperature is same, pressure will be same. Now when one bulb is kept at a temperature of 600 Kelvin, what will happen? From this molecules get diffused from hot bulb to the cold bulb. When two flasks are maintained at a different temperature, what will happen? The gas molecules get diffused from hot bulb to the colder bulb. Now colder bulb will have the higher number of the moles than the hot bulb. Due to the presence of excess number of the bulbs in the colder bulb than the hotter bulb, the pressure in both the bulbs will be maintained as same, and it is always already mentioned that volume is maintained constant. Now what is the point? When pressure and volumes are kept constant, what will be the relation we have? N1 T1 is equal to N2 T2. So N1 plus N2 is equal to 9. N1 plus N2 is equal to 9. If N1 is equal to X, what will be the N2 value? 9 minus X. What will be the N2 value? 9 minus X. So try to understand the concept clearly. Why initially both the bulbs are maintained at the same temperature, both the flasks will have equal number of the moles. When one flask is maintained at high temperature, diffusion takes place from hotter bulb to the colder bulb. Now colder bulb will have higher number of the moles than the hot bulb. As a result of higher number of the moles, in both the bulbs the pressure will be maintained constant, volume is maintained constant. Then what will be the relation? We can have N1 T1 is equal to N2 T2. What is given? N1 plus N2 is equal to 9. Let N1 is equal to X, N2 will be equal to 9 minus X. Now what is N1? X. What is T1? 300. What is T1? 300. What is N2? 9 minus X. 9 minus X. 9 minus X. What is T2? 600. Solving X will be equal to 6. And what is the number of the moles in the hot bulb? Number of moles in the hot bulb is, number of moles in the hot bulb will be equal to 9 minus X, 9 minus X, that is equal to 3. So option 4 is the answer. Option 4 is the answer. Next question. Now pressure of 1 gram of an ideal gas at 27 degrees centigrade is found to be 2 bar when 2 grams of another ideal gas is introduced in the same flask at the same temperature. The pressure becomes 3 bar. Then what is the ratio of MB by MA? What is the ratio of MB by MA? Now coming to the point, pressure due to when A alone is present, what is the pressure? 2 bar. When B is introduced, what is the pressure? PA plus PB has become 3 bar. What does it imply? Pressure due to the B is equal to 1 bar. Is equal to 1 bar. Pressure due to B is equal to 1 bar. Now coming to the PA by PB is equal to PA by PB is equal to NA RT by V by NB RT by V. NB RT by V. What are kept constant here? Temperature, volumes are constant. So this is cancelled out. What is NA? What is NA? PA by PB. PA by PB. This ratio is 2 by 1. And weight of A, 1 gram of A by MA. MA. What is that? MB. What is the weight of B? 2 grams. So MB by MA will be equal to 4 by 1. Simple ideal gas equation. Next question. The mass of molecule A is twice the mass of the molecule B. The molecular velocity of A is twice the molecular velocity of B, RMS velocity of B. If two samples of A and B contain same number of the molecules, what will be the ratio of the pressures of the two sample? What is the question? PA by PB is equal to how much? PA by PB is equal to how much? Here we have to use the kinetic gas equation, not ideal gas equation, because if you carefully observe the terms that are involved in the problem, so RMS velocity is there, number of molecules is there, mass is there. And what is the equation that connects mass, number of molecules and RMS velocity? Nothing but kinetic gas equation. So PA by PB is equal to Mn Ma Na Ca square by Mb Nb Cb square. Since number of molecules are same, this gets cancelled out. Mass of A is twice the mass of B. So 2 into 2 square by 1 into 1 square. So PA by PB will be equal to 8:1. 8:1. Got this point clear? Why we are using this kinetic gas equation? Because what are the parameters that are involved here? Mass, number of molecules and RMS velocity and pressure. What is the equation that connects all these parameters? Nothing but kinetic gas equation. Now what is the point? What is the thing? RMS velocity of the any gas is given by the expression. For that matter, C is proportional to square root of T by M. C is proportional to square root of T by M. When temperature is maintained constant, when the temperature is doubled and the molecules are dissociated into individual atoms. Now the RMS velocity of the nitrogen atom is x into v centimeters per second. And what is the value of the nitrogen? Now what is the expression for C is equal to root 3 RT by m? So C1 by C2 is equal to root of T1 by M1 into M2 by T2. What is C1? V. What is C1? V. What is we have to find? C2. So here if T1 is 1, and what will be the T2 value? 2. What will be the T2 value? 2. And what will be the M2 value? Due to the dissociation, molecular weight will be reduced to half. The molecules are dissociated into the individual atoms. The molecular mass will be reduced to the half. M2 will be equal to m by 2. M2 will be equal to m by 2, and m1 is equal to m, cancels out. So 1 by 2. So C2 is equal to 2V, therefore x is equal to 2. What happened? Temperature got doubled, molecular mass is reduced to half. Then what will happen to the RMS velocity? It gets doubled. X is equal to 2. Next question. A vessel contains equal weights of helium and methane gases at 20 bar pressure. Now what is the question here? Ratio of diffusion or of rate of diffusion of helium by rate of diffusion of methane will be equal to partial pressure of the hydrogen by partial pressure of the methane into molecular weight of CH4 by molecular weight of helium. What is the mole ratio of helium and methane? X by 4, since x by 16. So what will be the mole ratio? 4:1. What are the mole fractions? Mole fraction of helium is 4 by 5, and partial pressure of helium is 4 by 5 into 20, 16. Automatically partial pressure of methane will be 4, because total pressure is 20 bars. Now what is the ratio? Or 16 by 4 into 16 by 4. The value comes to 8:1.